Hello and welcome to this SAS Global Forum 2020 pre-conference tutorial on state space modeling. I am Rajesh Selukar, a statistician developer at SAS. In over 2 decades of work at SAS, I have developed software for many different areas of time series analysis and forecasting. As a part of this work, I have also authored two procedures, PROC SSM and PROC UCM, which are used for state space model based data analysis.
I have divided this tutorial into three sections. The first section introduces the state space model and the two SAS procedures, PROC UCM and PROC SSM, that are specially designed for state space model. The second section shows you where to look for additional information. Basically, we quickly go over the web links for the documentation of the UCM and SSM procedures and the books and articles I have found useful. Finally, in the last section, we will cover some interesting examples of state space modeling. Strictly speaking, the models discussed in this tutorial are called linear Gaussian state space models. In fact, there are other state space models, more general, such as nonlinear and non-Gaussian state space models. However, we will not discuss them in this tutorial. From now on, a state space model, or SSM for short, will always mean a linear Gaussian state space model. Historically, SSMs were developed to deal with engineering applications such as digital signal processing and system control. In the last few decades, they have found uses in other fields such as econometrics, social and environmental sciences, and many more. In these other fields, SSM is primarily seen as an adaptation of linear regression for sequential data, where the regression vector evolves with time as an autoregression. In this tutorial, we will emphasize this regression-centric view of SSMs. As a model class, SSM is very rich. For example, it encompasses most popular time series and longitudinal data models. SSM-based analysis is applicable whenever the data consists of one or more continuous response variables and possibly some predictor variables recorded over time. When we do have such a sequence of observations, the data analysis can have many goals. A few of these are listed below. For example, you may want to forecast the future values of the response sequence, or you may want to discover the underlying patterns such as trends and seasons. For all these and many more, an SSM-based analysis can be very useful. An SSM is defined by a set of three equations. The first equation, called the observation equation, writes the response vector at time t, yt, as a sum of three terms. The first term, xt beta, is the usual regression effect with xt as the design matrix at time t and beta the regression coefficient vector. So xt is the design matrix and beta is the regression coefficient. The second term, zt alpha t, is also similar, but in this case, the regression coefficient alpha t is time varying. So this regression coefficient is not static. It can vary with time. This time varying regression coefficient vector is called the state vector. The third term, epsilon t, is the usual noise term. it is modeled as a zero mean Gaussian vector. So the second equation, the state transition equation, describes the evolution of the state vector. According to this equation, the state at time t plus 1 is a sum of two terms. In the first term, the state vector at time t, the state vector at time t is multiplied by a matrix T sub t. This matrix Tt is called the state transition matrix. The second term, Ct plus 1, is the disturbance or noise term. This is also modeled as a zero mean Gaussian vector. The last equation defines the initial condition for the state transition equation. It specifies that alpha 1, the state vector at time 1, is a Gaussian vector with mean A1 delta. Finally, let me summarize the overall setup. Here, so yt is a sequence of responses, possibly vector value. Xt is a sequence of predictor variable vectors. Epsilon t and ct are independent zero mean Gaussian noise sequences. They are also called disturbance sequences, disturbance variables. Alpha t, also called the states, beta and delta, are regression-like vectors. The matrices zt, tt, covariances of the disturbances like covariance of epsilon t, covariance of state disturbance ct, and a1, which appears in the initial condition, are called system matrices. The system matrices are mostly known but can depend on some tuning parameters also. A1 is always fully known. A1 is usually an identity matrix or is a matrix made up of columns of identity matrix. If you are new to this type of model, it can appear rather complex. However, I assure you that after seeing some concrete example, it will start making sense. In the next few slides, we will see some concrete examples of SSMs. These SSMs are good starting examples, and they also form the building blocks of more complex models we will see later. So let's see the first example of an SSM. Random walk plus noise model is very handy to describe a random quantity with slowly changing mean. For example, suppose yt denotes a two-dimensional vector that contains my systolic and diastolic blood pressure measured at time t. So suppose this bivariate yt contains my systolic and diastolic blood pressure measurements. We can write yt as sum of two parts, alpha t, my true blood pressure at time t, and epsilon t, the measurement error associated with my BP measuring instrument. Assuming that my health remains constant or I remain healthy during the observation process, we can model the time evolution of alpha t as a random walk. That is, state alpha at time t plus 1, that is my true BP at time t plus 1, is a perturbation of my previous blood pressure by a random quantity, a random amount. So such a model is called a random walk. If my blood pressure doesn't have a upward or a downward trend, this is a reasonable model for blood pressure. The model for alpha t is completed by assuming that alpha 1, my true blood pressure at the start of the observations as some unknown vector delta. This is the initial condition. Now let us see what are the different system matrices in this simple SSM. Since Zt alpha t term in the first equation is simply alpha t, the system matrix Zt in this case is identity. Similarly, the Tt alpha t term in the state equation is also just alpha t. So the transition matrix Tt is also identity. Clearly, the A1 matrix in the initial condition is also an identity. The only non-trivial system matrices in this SSM are the observation noise covariance sigma epsilon and the state disturbance covariance sigma c. We are assuming that epsilon t and ct are IID disturbances. Such sequences are also called white noise sequences. Note that all the system matrices in this model are time invariant. In more general SSMs, these can be time varying. Before I finish with this example, let me point out two important special cases of this model. If the state disturbance sigma c is a zero matrix, that is basically these state disturbances are themselves zero, then the state equation becomes alpha t plus 1 equals alpha t. That means the state essentially is time invariant. All states are equal to the initial state delta. This means the entire model reduces to yt equals delta plus epsilon. That is yt equals constant plus error. So this is a constant plus error is a special case of random walk plus noise model. There are many other interesting special cases, but I'm going to point out only one more. Since my systolic and diastolic blood pressures are affected by the same process inside my body, it is conceivable that the state disturbance Ct is actually a scaled version of some one-dimensional disturbance. That is, instead of Ct plus 1 being truly two-dimensional, it is actually a vector, a deterministic vector times a one-dimensional random quantity. That is, in other words, the state covariance, the disturbance covariance of the state disturbances is of rank 1 rather than rank 2. Econometricians call such random walk a co-integrated process. That is, such a model is conceivable when the two processes in this two-dimensional random walk are actually more have some a common trend, and they are a manifestation of a common trend. Okay, there are several other interesting submodels of this random walk plus noise model, but we don't have time to discuss all of them right now. Let's move on to a another useful state space model. In this slide, we consider a process whose mean pattern is sinusoidal. In the earlier case, the mean pattern was a slowly varying pattern without any particular shape. Here, we are considering a mean pattern that is sinusoidal. The plot shown in the slide illustrates such a process. For example, in this plot, we have round circles which are observations yt, and a connected curve, sinusoidal curve, which is the mean of this process. Note that the curve in the plot is not a perfect sinusoid. Its shape gradually changes over time. For example, the first peak here is taller than the third peak. Such a time-varying sinusoidal pattern is called a stochastic cycle. In real life, we rarely see perfect sinusoids. So they change over time because of many other disturbances. They look like sinusoids, but the shape doesn't remain exactly the same as time goes on. It turns out that a stochastic cycle like this can be written as Z alpha t for a suitable two-dimensional state vector alpha t. Thus, the state alpha t represents a point on the circle at time t. According to the state transition equation, the state at time t plus 1 is obtained by rotating the alpha t point on the circle by a fixed angle. This is because this transition matrix, which is given here, is the so-called rotation matrix. It rotates a point on the circle by a fixed angle. Because of the disturbance term in the transition equation, the rotation is slightly perturbed. This gives rise to the time-varying sinusoidal pattern. So, if this disturbance term had not been here, then this sinusoidal pattern in the plot would have been a perfect sinusoidal pattern. But because of this disturbance term, the shape of this sinusoid changes over time as either a larger disturbance is added or a smaller disturbance is added. For added modeling flexibility, a damping factor rho is included in the model. A damped cycle represents a sinusoidal pattern that eventually dies out. That is, it dies down to zero. When rho equal to 1 and there is no disturbance in the state equation, we get the perfect sinusoidal pattern. That is the cosine curve. Or just to summarize, let me point out the four parameters in this model. The defining parameters of this model are lambda, the frequency of the cycle, or equivalently the period 2 pi over lambda, the damping factor rho, the covariance or the variance of the state disturbance sigma square c, and the variance of the noise, observation noise, epsilon t. These are the four parameters of this state space model. This is a state space model of dimension 2, state dimension 2, and in the observation equation, z alpha t term actually basically picks out the first element of alpha t, like the x coordinate of the point on the circle. So as the point is rotated around the circle, the x coordinate goes up and down. It could be x or y coordinate, it doesn't matter. But the and that up and down is what generates the cyclical pattern. Okay, so stochastic cycle is an important building block for a building block model in SSM uh, literature. As a last example of an SSM, let's consider stochastic seasonal patterns. A seasonal pattern is a periodic pattern of general shape. That is, instead of having a periodic pattern with a very well-defined shape like sinusoidal shape, this is a periodic pattern of more general shape. That is, it repeats itself every k periods, say, but the pattern of these k time points is not very well defined like a sinusoidal. In order to define or represent such a general periodic pattern, it's useful to remember a fact from Fourier analysis. A periodic sequence with period k can always be created as a sum of k over 2 undamped cycles of appropriate periods. So, for example, if gamma t is a periodic pattern of period k, then we can always write it as sum of some psi1 t plus psi2 t plus up to psi k over t to each of these psi's are cycles or sinusoids of appropriate periods. These constituent cycles are called harmonics. For example, a seasonal pattern of length 12, say, which corresponds to monthly seasonality, can be created by adding 6 cycles of periods 12, 6, 4, 3, 2.4, and 2. If the season period k is an odd integer, then k over 2 is rounded down. For example, if season length k is 7, then it can be represented as sum of 3 cycles. You can create a stochastic seasonal pattern that changes over the years by combining undamped stochastic cycles. That is, if you want to get a perfectly repeating periodic pattern, you add perfect sinusoids. If you want a slowly changing periodic pattern, then you add stochastic cycles instead of deterministic cycles. You can control the variation of the seasonal pattern by controlling the disturbance variances of the constituent cycles. As if you recall, a cycle, a, a stochastic cycle, its variation over time is controlled by its variance of its disturbance term. So similar thing happens with a stochastic seasonal pattern. You can control its variation time over time by controlling the disturbance variances of the constituent cycles. You can control the smoothness of the seasonal pattern by dropping the high frequency harmonics. For example, in a monthly seasonal pattern, if we drop the high frequency harmonics corresponding to periods 2.4 and 2, we get a smoother monthly periodic pattern. We get it even smoother if we drop a cycle with period 3 from the harmonic corresponding to period 3 from the representation. So this way we can create a slowly changing seasonal pattern of desired smoothness and desired variability. So this is a very flexible model for generating time varying seasonal patterns. Having seen some simple state space models, it's now time to move on to a little bit more complex state space models. In practice, we often need to model phenomena that are more complex than the example models we have seen so far. For such situations, suitable models can be formulated by combining appropriate submodels. In effect, one starts by postulating that the response sequence yt is a sum of some well-chosen components such as, say, trend mu-t, season psi-t, some cycles, regression effects xt beta, and noise epsilon t. Although not obvious at first, this model equation is in fact an observation equation of an SSM. In order to see this, we just have to realize that these components that we have included in the model equation themselves have state space form. For example, if this mu-t were to be a random walk model, we already know its state space form. We know how its state looks like, how its state evolves. That is, we know its transition equation, we know its initial condition. Similarly, if psi-t is a cycle, then we know its state space form. We know how its state vector looks like, how its transition matrix looks like. So these component terms actually define a larger state space model. So if we consider a state space model by augmenting these state sections, the first section corresponding to the first component, second section corresponding to the second component, third section corresponding to a third component if it's present. Similarly, we can form the system matrix ZT by creating a block matrix Z1T and Z2T. Similarly, the transition matrix can be created by a block diagonal matrix with blocks T1, T2, and so on. So the components define a augmented state space form, and the entire model can be put in our usual state space form. The representation of SSM in such a component form is called an unobserved components model. So unobserved components model is just a different way of specifying an SSM. This way of specifying SSM is easier because we can, by looking at by plotting the response sequence, or because we have the domain knowledge about the response sequence, we can postulate an appropriate model that contains proper explanatory variables or the predictor variables, proper trend terms, proper periodic terms, and proper type of noise. So this is how an SSM is formulated in practice. This is a very much regression-like approach of formulating a model. Finally, I will conclude the introduction part of this tutorial, or the introduction to the SSM part of this tutorial, by describing the output of a typical analysis, SSM-based analysis. So for example, after you have postulated an SSM or a UCM, you can use procedures like UCM and SSM for model fitting. The following list shows the main sections of the output produced by these UCM and SSM procedures. These procedures will give you estimates of model parameters such as the estimates of cycle frequency, disturbance variances, and the regression vector beta. You will get forecasts and interpolated values of the response variables. You'll also get forecasts and in-sample estimates of the latent components such as mu t, psi t, or whichever components are present in the model. It is very useful to plot and look at these components, estimated components, because just like in regression, we can decide whether a component conforms to our expectations and it can be dropped if it is insignificant. In general, this UCM is a very expressive form of time series modeling. Similarly, estimates of the linear combinations of these components can also be estimated. For example, you can have estimate of trend plus cycle. You might think, what's so difficult? Once we know mu t and psi t, what's the problem with getting estimate of mu t plus psi t? Actually, of course, the estimate of mu t plus psi t is just sum of estimate of mu t and psi t. But the standard error of these estimates are more difficult to compute because mu t estimated mu t and psi t are correlated estimates. So the in addition to the estimate of mu t plus psi t, you also get standard errors of these estimates. In the output, you also get model residuals and the residual diagnostics. You get model likelihood and likelihood based information criteria such as AIC and BIC, which are useful for model comparison, and also structural break diagnostics and many other things. After that brief introduction to SSMs, let us look at the capabilities of PROC UCM, which is designed for univariate time series modeling. By univariate time series, I mean you are studying a single response variable y, which is recorded at a regular interval such as daily, weekly, or monthly. As an example, suppose y denotes a daily electricity demand at a utility between 10 to 11 am. Of course, the utility is producing the electricity at all hours of the day, but we are focusing on this hour only. Depending on the location and the customer base of this utility, this daily demand will exhibit a variety of time series patterns. For example, the demand over time could be trending upward, downward, or somewhere in between. It may show day of the week seasonality. There could be holiday effects. The weather, particularly the temperature, could also be a factor. Therefore, a model for such time series must be able to account for all these different features. With the UCM procedure, it is quite easy to build a comprehensive model for such situations. It provides a rich collection of easy, ready-to-use components that can capture a wide variety of time series patterns. For example, you can use different types of trends such as random walk, local linear, and many others. You can use many types of periodic patterns such as stochastic cycles and seasons, and they can be finely and you can finely control their characteristics. It also offers many ways to incorporate regression effects. For example, spline regression for nonlinear behavior and transfer regression to capture delayed effects. That means the effects associated with lagged regression values. Finally, you can incorporate more general components such as ARMA noise. Usually, a simple white noise term is used, but you can also incorporate more complex noise patterns. It of course provides very rich output that I mentioned earlier. For an illustration of PROC UCM, I have chosen a case study from a book by Pelagatti. This case study deals with the modeling of hourly electricity demand in Italy. 9 years of hourly electricity demand history is available for model development. From the modeling perspective, these data are quite interesting. They exhibit several different types of seasonal behavior at different scales, and the demand on holidays is usually different than other days. The plot on this slide illustrates some of this behavior. In order to keep things simple, I have chosen to display only a small portion of the data. The demand during the hours of 10 a.m. in the morning and 10 p.m. in the night is shown for the years of 2007 and 2008. From the plot, you can see that the 10 a.m. demand and the 10 p.m. demand have similar patterns, except that the morning demand is higher than the night. Although not easy to see, the dominant periodic pattern in the plot is the result of the day of the week seasonality. You can also see a month of the year pattern. For example, the electricity demand during August is quite low compared to other months for both year 2007 and 2008. This is because it is a vacation month for many Italians. Now let us see how to model these data. Modeling hourly electricity demand is a well-studied problem, and many different time series models have been proposed. You can use the UCM procedure to fit most of these models. For now, however, we will follow the modeling strategy suggested in Pelagatti's book. As per this strategy, we treat these hourly data as a collection of 24 daily time series, one for each hour of the day. For each series, the electricity load is decomposed into 5 terms. Mu t denotes a random walk trend. Xt beta is a correction for the holidays, such as Christmas and New Year. Gamma 7 is a day of the week effect modeled as a trigonometric season of length 7. For added modeling flexibility, the 3 constituent harmonics in this season can have their own disturbance variance parameter. Gamma 365 is a day of the year effect modeled as a trigonometric season of length 365. For reasons of parsimony, only the first 16 constituent harmonics are included, and all of them share the same disturbance variance parameter. Remember that a season of length 365 is the constituent harmonics are nearly 180. So we are only taking the first 16 of them. So this will be a fairly smooth seasonal component. Finally, epsilon denotes the noise term, which is modeled as a simple white noise. In order to use PROC UCM to model these data, an input data set, say load, is created. Since the demand for each hour of the day is treated as a separate series, the hour of the day is used as a bigroup variable. Within each bigroup, the data are sorted according to the date of the observation. So this is the ID variable, date, and its interval is day. Additionally, dummy variables corresponding to the desired holidays are included in the data set. These are a day before Christmas, Christmas, and so on. Suppose the name of the electricity demand variable in this data set is E-load. So E-load is the demand variable. Now we can specify the model we want to fit. The response variable and the simple regressors are specified in the model statement. So this model statement specifies what is the response variable and what are the simple regression variables in your model. So this xt beta term is specified by specifying these regressors, and load t is this variable eload. The gamma 7 effect, the day of the week effect, is included by specifying three constituent harmonics in this season. These three cycle statements are these three harmonics. The first harmonic of period 7, these are undamped cycles, so rho is equal to 1, and these are held fixed. The period is held fixed at 7 and the damping factor rho is held fixed at rho equals 1, and no est means don't estimate these parameters. Keep them at their stated values. The third parameter of this cycle, the disturbance variance, is left unspecified and will be estimated using the data. So this finishes the specification of the gamma 7 term. These three cycles together make up this gamma 7 term. The gamma 365 term, which is a season of length 365, is specified by this season statement. In UCM, if the constituent harmonics of a stochastic season share the same disturbance variance parameter, it can be specified more easily by the season statement. So this is how, and the fact that we are only using the first 16 harmonics is specified by this keep harmonics option. If this keep harmonics option is absent, then all harmonics of this trigonometric season are used. This finishes the irregular statement component is specified by the noise component is specified by the irregular statement, and the random walk trend is specified by the level statement. So irregular, level, 3 cycle, and the season statement and the model statement. This is the model specification part. Now the estimate statement controls the parameter estimation aspects of the problem. So back equals 14 option in this statement says that the last 14 observations in the data be not used during parameter estimation. And the plot equals panel option says that produces a panel of residual diagnostic plots. Similarly, the forecast statement controls different aspects of the forecasting output. In this case, the two options back equals 14 and lead equals 14 cause the last 14 observations to be used for forecast validation. The out for equals option specifies an output data to store the forecasts of the response series and model components. This entire model fitting for this 24 series takes about 15 minutes to finish. This is a fairly large data set and many parameters to estimate. So it takes a little time, but in 15 minutes, all these more than 70,000 observations are processed. This slide shows the time series plots of the components estimated for the 10 AM series. For easy viewing, only a small section of each plot is shown. Note that the horizontal axis for the gamma 7 component spans only a few weeks in 2006 through 2007 year, whereas all other plots show the span of the entire 2007 to 2008 year. So all these three other plots, the x-axis spans 2007 to 2008 year daily points. The, the vertical axis in these plots, however, differ in scale. For example, this vertical axis goes from 41,000 to 45,000, whereas this y-axis goes from minus 15,000 to plus 5,000. The irregular component, where the vertical axis varies between minus 2,000 to plus 3,000. So the variation on the vertical side, pay attention, they are not on the same scale. Such plots are very useful to understand the contribution of each component to the model, as well as whether their patterns conform to our expectations. For example, the trend plot shows that the mean demand varies around 43,000 units. The plot of the day of the week season shows pronounced differences between different days of the week, and for example, this is the lower part, the lowest demand day, this is the highest demand day, and so on. And on low demand days, the demand goes down by as much as 13,000 units, so it can go down as much as even 14,000. The day of the month plot shows that for the month of August, the demand can go down by about 10,000 units. Comparing with the trend plot, they are one below the other. It appears that the correction for the August month could be improved slightly, maybe by adding a few more harmonics in the definition of the season. The look at the plot of the error component suggests that the model fit for the month of August needs some improvement. This is the month of August. This slide shows a panel of residual diagnostic plots and the time series plot of the series forecast in the validation period. So the residual diagnostic plots are in the left panel and the forecast plot is in the right panel. This series has more than 3,000 data points. So the visual inspection of residual diagnostic plots can be tricky. For example, the QQ plot is easily distorted by a few outlying points, and the bounds around the autocorrelation and partial autocorrelation plots can be overly tight. The histogram of the residuals is kind of okay. So on the whole, there is not the residual diagnostics doesn't show very alarming deviations from our model assumptions. Although this might be debatable. The forecasts in the validation period indicate that the model may be useful for forecast in the short horizon. For example, most of the observed demand seems to follow the forecast pattern. So, of course, in the real modeling situations, one would do a lot more model checking. For now, we will stop here. As mentioned earlier, temperature can be an important driver for the electricity demand. The relationship between temperature and demand is usually nonlinear. The demand is higher during hot summer as well as in cold winter days. In the case study data we modeled earlier, temperature information was not available. If such temperature data were available, the earlier model can be augmented by adding a term for nonlinear temperature effect. So the earlier model could have been augmented with a nonlinear temperature effect. This code segment shows you how to do that. Suppose the temp load data set is the load data set with additional variable temp, which indicates the ambient temperature. You can include the nonlinear temperature effect in the model by using the spline reg statement. So in the spline reg statement, you specify the variable that you think has a nonlinear effect on the response variable. The spline reg statement shown here creates a cubic spline. So degree equals 3 says that we want a cubic spline with 10 evenly spread knots in the observed temperature range seen in the dataset. So this statement creates an appropriate spline term which will add a nonlinear temperature effect to our load model. Even though we don't have the temperature data for the case study, an example in the UCM documentation illustrates a similar analysis on a different electricity demand dataset that does have temperature information. For these data, the left panel shows the scatter plot of temperature versus electricity demand. So this is the average daily temperature observed in that dataset, and this is the electricity demand on those days. So the the relationship between temperature and demand seems to be this non-linear relation. For during the pleasant temperatures of 50 to 60 degrees Fahrenheit or between 50 to 70, the demand is lower, whereas it increases as the temperature goes up or as the temperature goes down. The right-hand side plot shows the estimated temperature effect obtained by including a spline term in the model. The spline term is included in the model the way we saw in the last slide. And as you can see, the estimated temperature effect is very similar to what the scatter plot shows. So that means we clearly got this term right. With this, we complete the discussion of the UCM procedure. The rest of the tutorial illustrates the capabilities of the SSM procedure. PROC SSM is designed for general state space modeling. Unlike PROC UCM, which is designed for univariate time series modeling, PROC SSM can handle very general types of sequential data. For example, with PROC SSM, you can analyze univariate and multivariate time series, panels of univariate and multivariate time series, and univariate and multivariate longitudinal data. Longitudinal data are sequential but not necessarily equally spaced in time. PROC SSM syntax enables you to easily specify very general, possibly non-standard SSMs as well as many important standard SSMs such as ARIMA, Univariate and multivariate UCMs and many more. Like PROC UCM, PROC SSM also provides rich tabular and graphical output. In this slide, we will go over the PROC SSM statements that are used for model specification. Suppose that we want to specify a model y equals x beta plus mu t plus psi t plus some other components plus r. And suppose that each of these components has some underlying state space model with its observation equation, transition equations, its own system matrices. Each one of them has its own state, and the overall state is formed by combining these state subvectors as we saw earlier. So the question is, how can we specify such a model by using the SSM syntax? First, note that the model specification statements are designed such that Many commonly needed model parts, such as different types of univariate and multivariate trends, cycles, seasons, and noise models, can be easily specified by using keyword-based syntax. Also, simpler subspecifications can be combined to form more complex subspecifications. And most importantly, you can use data step language for defining system matrices, and you can define regressors on the fly using data step. With this feature, you can specify arbitrarily complex SSMs. Now let us look at the individual statements. So let's begin with the ID statement. The ID statement is used to specify the time index variable. When the data are not simple time series and when the system matrices are time dependent, the ID variable can be an important part of the model specification. For example, in many longitudinal data cases, the transition matrix elements are functions of the distance between successive time points. The PALM statement is used to specify parameters needed for the user-defined components. So we'll see several examples of that. So I will explain it later more. The next statement, the state statement, is used to specify the transition equation of a state subvector such as alpha 2. So for example, alpha 2 or alpha 1. Using the options in the state statement, you can specify highly complex state transition equations. So we'll see the examples of these also later. The component statement is used to specify a component associated with a previously defined state subvector. For example, if you have defined alpha 2 using the state before, you can use this definition of alpha 2 to define a component based on that. So for example, the definition of psi as a dot product of Z2 and alpha 2 will be defined in the component statement. That is, with every component term in the model, there is an associated state and component pair. Okay. The next statement, the trend statement, simplifies component specification for some commonly needed component types. For example, components like random walk and ARMA noise can be specified by using keywords. In effect, the trend statement does the appropriate state component pairing behind the scene. So for example, mu or psi happen to be components that have keyword support in the SSM procedure, then you don't need the state and component pair for them. You can just use one trend statement to specify that with a keyword. The next statement, the dep lag statement, is used to add lagged response variable terms in the model. The irregular statement is used to specify the noise term in the observation equation. And finally, the model statement is used to specify the observation equation of a response variable. In multivariate case, a separate model statement is needed for each response variable. So in a model statement, you specify the response variable, one for each response variable, if this y happens to be a multivariate vector. And you specify the regression variables, you specify the components that you have defined before, and that completes the model specification. As mentioned earlier, the data step statements can be used to specify the elements of system matrices like Z, the transition matrix, and the disturbance covariances, and so forth. For defining these elements, you can use the data step programming statements such as array, do, if, then, and else, and mathematical functions to create system matrices. Okay. We'll see the examples of these soon. In fact, let us see a simple example of specifying an SSM using the PROC SSM syntax. So suppose we have a univariate model y equal to a regression variable effect, a random walk trend, a cycle, and noise. In SSM procedure, there is keyword support for all the components in this model. However, for illustration purposes, let's specify the cycle component without using the keyword support. Recall the dynamics of the two-dimensional state associated with an undamped cycle. We can specify it as follows. So remember our stochastic cycle definition. So cycle can be defined as a dot product between a vector z 1 0 and a two-dimensional state alpha t, and this two-dimensional state has this transition equation with transition matrix T as a rotation matrix, this rotation matrix. And the disturbance variances have a diagonal covariance. In fact, the covariance is like sigma squared C times identity matrix. Its initial condition is quite simple. Alpha 1 equals delta, with basically the A1 matrix in the initial condition is simply identity. So we will specify a model with a regression variable, a random walk trend, a cycle, and a noise component. So let's begin the specification of the cycle component. The first two palm statements define lambda and this lambda and sigma squared c. This CR corresponds to this sigma squared c parameter. So by the definition of lambda, it ranges between a lower bound of a number close to 0 and an upper bound near pi. So the lambda ranges between 0 to pi as we want it. The variance parameter C bar has a lower bound of 0. So, and then we define the transition matrix T, the 2 by 2 matrix, as an array of 4 elements, A1 through A4. And in SSM procedure, when an array defines a matrix, it's read row-wise. So the A1 and A2 define the first row, and A3 and A4 define the second row. So A1 is cos lambda, A2 is sin lambda, A3 is minus A2, and A4 is A1. So the transition matrix of the cycle component is defined using these programming statements. Now the state statement actually defines the transition equation of this cycle component. So the state statement says consider a state section called cycle state, and this state section is of dimension 2. Its transition matrix is of general shape G, signified by G, and its elements are given by the array cycle T. Similarly, the disturbance covariance is of identity type multiplied by a variable C bar in this case. The initial condition is specified, the matrix A1 in the initial condition is specified as A12. It essentially in this case means it's an identity matrix of size 2. Finally, the cycle specification is completed by writing the specifying the corresponding component statement. which says that the cycle component is a dot product of a vector z and the state section alpha. So this component statement says that let's define a component called cycle, which is the dot product 10 times the cycle state. Thirdly, we are going to use keyword specification for the random walk trend. So that is specified using the trend statement that says random walk is a random walk. So random walk is just a name, and the keyword specification RW says that it's actually a random walk. The irregular component is specified like this. It names white noise as, again, internally it's modeled as white noise. So finally, the model is specified by the response variable, the X variable as a regressor, random walk, cycle, and white noise are the other components to be included in the model. So that finishes the model specification part. This kind of finishes the introductory part of the PROC SSM, the introductory discussion about the PROC SSM. Shortly, we will see several concrete data analysis examples using PROC SSM. However, prior to that, let us see where you can get additional information about state space modeling, PROC UCM, and PROC SSM. SAS documentation, which is freely available, is a good starting point. The UCM and SSM procedures are part of SAS ETS. Let us quickly check the SSM documentation link. The documentation is divided into several parts. So the documentation link usually opens in the syntax section. We already have seen how the SSM procedure syntax looks like. So let's go to other parts. So the getting started example, getting started section contains an SSM-based analysis of a well-known panel dataset. So this section is a good section to start with. Then you'll see that the exact examples section has 18 more illustrations of SSM-based data analysis. So there are plenty of worked examples to both learn how to specify the model, the variety of situations you can use the SSM procedure, and many other things. We will go over some of these examples in this tutorial itself. The web-based documentation is very convenient. There is one more thing. It is better to use web-based documentation because you can get the latest documentation. And secondly, and in fact more importantly, the web-based documentation includes links for the example data and code. For example, the first example, which we will see later in the tutorial, you can just click on the code and data for this example. So as you can see, the data and the code associated with this example is shown there. You can just cut and paste this and run this example in your SAS editor. So this is a very useful and convenient feature of the web-based documentation, which if you download the PDF documentation, you'll have to especially go to this section later, to this code thing. There will be no link necessarily for the data and code for that example. Another important section is the details section. It has several sections explaining the theory behind the SSM procedure and a variety of things. Let me mention a few of these sections. This The state space model and notation section contains the precise form of the state space model that can be handled by PROC SSM. You will notice that this form is much more general than the form I used at the start of this tutorial. I used the simpler form to keep the notation simple. The filtering, smoothing, likelihood, and structural break detection section provides the details about the famous Kalman filtering and smoothing algorithm, which is the main computational tool for state space modeling. Other sections provide many other details, such as the precise forms of the keyword-based models supported by PROC SSM. So the documentation is a great resource. The reference section contain the important papers that are relevant for state space modeling. Okay, so let's go next. So in this references section, I'm going to I have listed the books that have greatly influenced the development of this procedure. For example, the first book by Durbin and Koopman contains rigorous treatment of linear SSMs in the first part. The second part and its second part deals with more general SSMs like nonlinear or non-Gaussian SSMs, which we are not going to discuss. The second book by Harvey is considered a classic in this field. It continues to be the go-to reference for univariate and multivariate UCMs. The book by Pelaghetti is the most recent and probably the best book to get started with this subject. So these three books are quite useful. And another thing is that I have sort of the syntax of the SSM procedure and even the topics that are dealt by using the SSM procedures are influenced by these books. So virtually every example in this book can be easily specified and modeled using the SSM syntax. The SAS global forums, the two SAS global forums I have mentioned here, also act like a addition to the UCM documentation. They deal with two important topics which are not usually covered in the SSM literature. So the topics are functional modeling of longitudinal data and detection and adjustment of structural breaks, all using the state space models. I think you will find these references, these books and references quite useful. Additionally, SAS Education Department regularly offers courses on state space modeling. For example, you can take the half-day course on PROC UCM and the 2-day course on PROC SSM. So these are offered regularly. You can check the schedule in the links that I have provided here. Now we will go over 4 illustrative examples of using PROC SSM. First 3 of these examples are part of the SSM documentation, and the last one is discussed in one of the global forum papers I have mentioned. Therefore, I am going to keep the discussion of these examples fairly brief. So in case I miss something, or you can always go back to this, either the documentation or that paper, and you will see all the details. Of course, you can write me if you still don't follow some of these things. These examples are meant to highlight the versatility of the SSM procedures. Sometimes you are going to get lost because these examples, at least one of them is kind of tedious, but bear with me. So let's start with a first example. In this example, let's look at the time series plot of a bivariate quarterly time series, which is observed from the first quarter of 1969 up to the last quarter of 1985. So these are the two time series. The response variables are FKSI, the blue line, and RKSI, the red line, and these represent the log of quarterly totals of the front seat and rear seat passenger injuries in UK. So the top line, the blue line, represents front seat passenger injuries, and the lower one represents the rear seat passenger injuries. And this vertical line, which is shown on the plot, signifies the introduction of a law, a seatbelt law that was introduced in the first quarter of 1983. By this law, the the front seat passengers were compelled to wear seat belts. So the goal of this study is to see if this law has been effective in reducing the front seat passenger injuries. In order to answer this question, one must understand the historical patterns of this bivariate series. So when we look at this series, we notice that both FKSI and RKSI have relatively flat trends and an obvious quarterly seasonality. It also appears that the two series move together, which is not surprising since an accident is likely to affect both the front and rear passengers also. It also appears that there is a drop in the FKSI level after the introduction of the seatbelt law. So, but the question is how significant it is statistically, and so on and so forth. We will consider a model that is consistent with these observations and see whether the drop is statistically significant. Now, here is the model that we consider for these series. So this is a bivariate series with the first element of the vector response vector FKSI, the second element of the response vector RKSI. And here is the regression term. So in the regression term, we have xt, which is basically an indicator of start of that seatbelt law. So it's 0 before 1983 Q1 and 1 thereafter. And this variable is supposed to affect only the FKSI, the front passenger. The rear passengers, the regression is 0. Then there is a bivariate random walk trend, because we saw the trend didn't have an obvious upward or a downward trend. So a random walk is a sufficient, is a reasonable trend model. And also, since I mentioned that these two series appear to, well, move together, we are going to put a restriction on the covariance of this, the disturbance covariance of this random walk. We'll see that in the model specification later. The third term is the seasonal term, the trigonometric seasonal term for quarterly seasonality. And the last one is a bivariate white noise. Okay, so let's see how to specify this in the SSM procedure. So the input data set is specified as seatbelt and it has the necessary information. The data are quarterly and the date variable in the data set indexes the time. Here is a data step statement that defines the variable xt that we need. It's defined on the fly using the date variable in the input data set. It says that basically this is, if this condition fails, that means if the date is before 1983 first quarter, then it's 0 and it is 1 thereafter. The first statement defines a two-dimensional component or state vector. It's of type white noise and it has general covariance. So its covariance is a 2 by 2 covariance. And wn1 and wn2 are first and second element of this error vector, and they define white noise components that will be used later in the definitions of models for FKSI and RKSI. Okay. Then we go on to define the trend component, which is called level in this, which is going to be random walk. Is defined by a state statement, and the state subsection is called level. It's also of dimension 2, and it's of type random walk. And we say that the disturbance covariance of this has rank 1, signifying that these two series kind of move together. And the first element of this random walk is called random walk 1, second random walk 2, and they again will be used in the observation equations for the response variable. Similarly, a state for the corresponding to the seasonal component, and here the type is season and the season length is 4. Okay, so that defines quarterly seasonality. Actually, here the disturbance covariance of the season term is set to be 0. That is, when it's left unspecified in this case, it means it's 0. It defines essentially a deterministic seasonality of length 4, because it turns out the seasonal component hardly changes in the history of this series that we have in our data set. Finally, let's see how the model is specified. So we need two model statements because we have bivariate series, and the first series, the FKSI, has this regression variable, and then the components that we have created. So, and the output for this of this analysis will be put in an output data set belt1. Actually, this procedure can produce a lot of graphical and printed output also, but to keep the syntax within this page, I have kept this very crisp and small. This output data set will contain estimates of all the components that are defined. For example, estimate of beta, estimates of mu t, ct, the noise, and in addition, we can define linear combinations of these components, which is defined. We want to define basically what is the seasonally adjusted series. A seasonally adjusted series in this case for FKSI would mean effect of xt beta plus mu t would mean a seasonally adjusted front passenger series. So we have defined a linear combination. The SA stands for seasonal adjustment. It's just a name, which is I want the procedure to estimate this sum. Okay, so and this will be output in the output data set. And here is the plot of this sum with its standard error or the confidence band and the series plotted around it. So you can see the seasonally adjusted component goes through the data points quite well, and you notice now the drop in the trend at after 1983 quite clearly. It turns out that the estimated beta parameter is negative 0.408 and its standard error is 0.025. So the drop is statistically significant. So this is how you can conduct a bivariate analysis of a bivariate series. We could have had much more general model. Okay, so now let's move to the next example. The model specification in our first example was relatively simple. All the model components could be specified using keyword support. The example we consider now is considerably more complex. So this example is going to be a little bit tedious to go through. I hope you will bear with me. So anyway, let's begin. In this example, we'll model the time evolution of the yields of government bonds of different maturities. That is, we will model the so-called yield surface. We have monthly data from January 1970 to December 2000 on bond yields of 17 bonds that range in maturities from 3 months to 10 years. Okay. As an illustration, the graph in this slide shows the yields of bonds of maturities 3, 60 and 120 months. So that is 3 months, 5 years and 10 years. So you can see how the bonds behave. Particularly in the early 90s, these bonds give very different yields, but in later years the yields are not so different. That is, the short-term bonds and the long-term bonds don't differ in the yields much in some later years, but earlier there is a good bit of difference. The goals of these, to be specific, let's suppose we have the following goals for our analysis. Goal 1, model the interrelationships between these 17 bonds of different maturities and produce short-term forecasts for the bond yields. And goal 2, which is somewhat, it's an important activity for hedge fund managers. Actually, the people who hedge, like the companies, they have to hedge their future risks. So the goal 2 is, using the fitted model, predict the yield of a hypothetical bond with a maturity of 42 months that is not traded on the general exchange. So a bank might issue such a thing to a company. They may get into an agreement over a bond of 42 months. Now what the question is, what should be the reasonable yields of such a bond? Yield surface modeling is an important problem for econometricians, and many models have been suggested. A model called dynamic Nelson-Siegel model, which has a few different variants, has shown good promise in this area. We will use PROC SSM to fit a version of this model. In order to specify this model, we will need some notation. Let yt tau denote the yield of a bond of maturity tau observed at time t. So t denotes the time index and tau denotes the maturity. We will consider an SSM for yt tau, which is based on a three-dimensional state alpha that follows a vector autoregression of order 1 with mean mu. So the state vector that underlies this SSM is three-dimensional. Its elements are alpha 1, alpha 2 and alpha 3, and we'll assume that this alpha t vector is a vector autoregression with mean mu. The observation equation of this model is a bit involved. So the observation is given here. So the observation equation has just two terms. One, which is a vector product of z and alpha, and other is the error. This error process, or the noise, its variance changes with the bond maturity. So for a bond for 3 months, there is a error variance associated with it. Bond for 6 months, there is different error variance associated with it. So for each different maturity, we'll assign a different error variance for the observation error. Secondly, the system matrix Z depends on two parameters: the maturity tau and a positive parameter called lambda. So let me explain this z vector. So the first element of this z vector is just 1. The second element of this z vector is a somewhat complicated function of lambda and tau, and z3 also is another function of lambda and tau. So in effect, by writing down the dot product fully, we get the observation equation for, so the yield at time t for a bond of maturity tau can be decomposed into this term, which represents, I'll explain this term. So these terms, 4 terms basically, 3 terms resulting from the this dot product and the noise term. Okay, so the first term, alpha 1t, is the overall yield at a given time point. So, and this doesn't depend on the maturity. It only depends on the time. It changes over time, but for a given time, it's just the bond yield for that time period. So, if I don't tell you the maturity of a bond, you would say probably its yield is alpha 1t. The The second term, Z2 tau times alpha 2t, is a correction for short-term bonds. Because this multiplier Z2 tau becomes small when tau is large. So for large bond maturities, this term becomes smaller. Similarly, the third term, Z3 tau, it's a correction term for medium term bonds. That means it's non-zero only when the bond maturity is of medium term. Other times, this term is negligible. Finally, this is the noise term. Okay, so this model has several parameters. The different parameters for the error variances for these 17 bonds, this lambda parameter which is involved in these elements of Z, and of course the transition equation of this alpha t I didn't mention, but it's a var process, so it's var1 process, so it has the AR1 matrix associated with it and the error covariance matrix. We'll later see that we will restrict the AR1 matrix to be diagonal, so it will, but still these are not univariate AR1 processes which are uncorrelated, but they will be correlated univariate AR1 processes. So these elements of alpha are correlated AR1 processes. Okay. The another thing to note, or a general comment to make, is that this model provides a probabilistic description of the behavior of bonds of all maturities, not just the ones available in our dataset. That is, it provides a model for the entire yield surface. So the tau here can be one of the bonds in the dataset, but it also postulates a model for bonds with other maturities. That is, it provides a model for the entire yield surface. This will help us achieve our 2 analysis goals. Extrapolate the observed bond yields into the future and interpolate the bond yields for the unobserved bond with maturity of 42 months. Note that we have 17 observed bonds and an unobserved bond we are interested in with the maturity of 42 months. The yields for the unobserved bond are set to missing. So the input data set will have cells for at every time there will be a cell for this unobserved bond yield, but it will be missing. After the model is fit, these missing values will be filled with the model-based predicted values. So that's our plan. Now, before we specify this model in PROC SSM, let's go over the organization of the input data set. The input data set has four variables. The date variable that indexes the model. On this slide, I am only giving you a, the, a portion of the syntax needed to specify this model. So basically the name of the input data set and other things are not shown here, just so that the syntax fits on this slide. So the date variable, the ID statement is not shown here. So ID statement will have a monthly date variable. The response variable is the yield. So this will eventually be specified in the model statement. So the yield is the bond yield, which is our response variable. And maturity, which indicates the bond maturity. So bond maturity is displayed or measured in months. So that column will have maturity associated with the bond. And a fourth variable, which is primarily included to help with some programming statements in the syntax. It sort of helps define some arrays that we need. That variable is called M type for maturity type. It's just a label variable. It indexes these 18 bonds, the first 17 bonds that we have observed, and the 18th bond we are interested in, an unobserved bond we are interested. So these bonds are just simply labeled as 1, 2, 3, 4, 5 up to 18, so that we can create some arrays later. Okay, so we have these four variables in the data set. Now we can begin, I can begin to explain the statements in the syntax and show you how that defines the model we are interested in. So the first few statements, these statements actually define the observation error. So eventually we are going to have an irregular statement which will define a white noise sequence that has variance sigma. But sigma is a variable that can change its value from row to row. So when a row represents a bond with certain maturity, this sigma would be a parameter associated with that maturity. So in order to do that, we have defined 17 variance parameters. Sorry, it's here in the PALM statement, and they are positive number. They should be positive, and this array simply has these 17 variables as elements of this array, so that we can say that sigma equals ith. When the bond type is I, then the sigma is that corresponding sigma I. Okay. For the 18th bond, which is the unobserved bond of maturity 42, we want its variance to be somewhat similar to the variances of its neighboring bonds. So arbitrarily, we have assigned its variance to be the average of the bond with maturity 36 and bond with maturity 48. These are the neighboring bonds around maturity 42. And so these statements create a white noise sequence with variances that change with maturity, not with the time. They are invariant as far as the time is concerned. Okay. Now we'll specify the z vector. So the z vector depends on a parameter positive parameter lambda, and then it also depends on the variable maturity, which is an input data set variable. So these statements define the z vector. Okay. So now this z vector, along with the three-dimensional autoregression, makes the first term of the observation equation. But rather than specifying the autoregression as a generic state space model, we'll use the keyword support available for VARMA models in SSM. But the VARMA model defined in the SSM syntax is always zero mean, the keyword supported VARMA model. So what we'll do is that we want a AR model, AR1 model with mean. So we'll divide the specification task into two steps. First one will define a var1 model with mean 0, and its mean will be defined as a three-dimensional random walk with 0 for the disturbance term. So it will be constant. So with this trick, these statements define the needed autoregressive term. So finally, the yield is defined as that the two components from the zero mean and mean part of the autoregression and the white noise. That completes the model specification. So this may appear a little bit complicated specification, but it shows you can do a number of things with these tools of data step states, the data step programming statements, and the palm variable, and so on. The palm statement, and so on. Now let's see some of the output. I'm not going to go over too much of this output. So this plot shows you the estimate of the overall yield, and it of course changes over time. So for example, in the mid 80s, the overall bonds yielded pretty high. The yield was more than 14%. In those days, actually, if you kept money in the bank, your savings account paid you 8-9% interest. And of course, as years go by, both the savings started paying less and the overall bond yields also went down. This shows you the estimated yield surface for the 3 months, 60 months, and 120 months. You can think of them as denoised yields. This plot is somewhat not very well done, I'm sorry, but there is actually a line. The crosses and pluses and circles are the actual observed yields, and there is a line going through them, which is the estimated yield. So, and then as you can see, after 2000, the yield surface is behaving somewhat interestingly. Maybe the inversion of yield curve. I'm not an economist, so I'm not going to say much. But the behavior appears interesting. And these are short-term bonds being compared with relatively long-term bonds of 5 years and 10 years. Okay. Finally, we'll see what are the predicted yields of a hypothetical bond of 42 months. So, and I have purposely plotted the neighboring observed bond yields, 36 and 48 months. And we would expect, if the model is doing a reasonable job, the yield of this hypothetical bond should be sandwiched between these yields. And that's what exactly is shown here. So the model, of course, I have not shown you much about this model, its residual analysis or many other things, but this is just to let you know it seems to behave as one would like it to behave, so far at least. Okay, so that finishes the second example. Let's go on to the third example. In this example, we consider the problem of creating a series of monthly GDP numbers that are consistent with the available information, such as the official GDP numbers, which are published only quarterly, and the industrial production numbers that are published monthly. So what we want to do is that since the GDP numbers, official GDP numbers are only published quarterly, but for variety of reasons, people need GDP numbers at finer intervals, for example, monthly. So this is called a temporal disaggregation or temporal distribution problem. And state space modeling is a popular choice to solve this problem because if a variable is modeled by an SSM at a particular time interval, for example, the GDP is modeled at say monthly interval, its aggregated form, for example, the quarterly form, also follows an SSM. So of course, we don't observe monthly GDP, but if we propose a model for monthly GDP, then a model for quarterly GDP can be deduced. Anyway, so this is a very useful property of SSM. So we are going to use this property of the state space models to in this temporal distribution problem. Let's denote the quarterly GDP which is observed as GDP and the unobserved monthly GDP, quarterly GDP as GDP dagger. The industrial production is denoted by a variable called INDPRO. So clearly by our definition, the observed GDP is sum of the unobserved GDP numbers. So for example, if this GDP is the March GDP, then this is March GDP, sorry, quarterly GDP published in March, then this should be sum of March's monthly GDP plus February GDP and January GDP. So January, February, March added together make the quarter ending in March. Okay. So our goal is to estimate these monthly GDP numbers using available information. So in this case, we also have information available on the monthly industrial production. So the input data set that we will consider has this form. So we have this date variable which indexes the monthly observations. The GDP variable, which is published quarterly, has missing values in the months where it's not published, and the value when it is published is non-missing like this. And monthly industrial production numbers, which are available every month. Okay. Also, we also have one additional variable, let's call it start Q. This variable is needed later in the SSM specification, model specification. It's a variable that indicates the start of the quarter. So in the case of quarters, it's very definite. Every quarter has only 3 months. But imagine if you had monthly data and you wanted to distribute it to daily data. In that case, each month has different numbers of days and things like that. So this variable is needed to basically indicate the start of the aggregation interval. Okay, so here the start Q variable is 1 when the quarter begins. Okay, the proposed model, we are going to propose a model for the bivariate series, industrial production and GDP dagger. So this is only a partially observed bivariate series because we don't really observe GDP. But a bivariate model for this partially observed series will actually imply another state space model for the fully observed bivariate series, industrial production and quarterly GDP. This implied model is not easy to describe, but you don't have to worry about it. This implied model will be fitted by the SSM procedure behind the scene. And so the SSM procedure will realize that you are actually specifying, even though you have a model for an aggregated form of variable. So it will formulate the implied SSM, do the necessary computations, and output the results for you. So let's first see what is the model we are specifying for the partially observed series. So this GDP and GDP dagger are assumed to be sum of a bivariate trend. In this case, this trend is an integrated random walk. I have not shown you the plots of GDP and industrial production, so you don't know the reasoning behind suggesting an integrated random walk as a trend. If you look at the plots, you'll see that the GDP is trending upward, and integrated random walk creates a smooth trend. Okay, so also there is a bivariate cycle, which is another term in the model, which captures like business cycles and things like that, and a bivariate white noise. So further information about this problem can be seen in example 16 of the documentation. And here is how we specify this model. So the model specification in this case is similar to other. We have already seen at least two examples of bivariate model specification, or maybe at least one full example of a bivariate model specification. So you start with a bivariate trend, bivariate cycle, bivariate noise. So these are model component specification for this bivariate series. But remember that this is an unobserved series, and we want actually model for the implied model for this. So the only difference is that, so in the model equations, this industrial production is an observed variable and it is not an integrated observed variable. But GDP, or I mean aggregated, GDP on the other hand is the observed variable, which is an aggregated version of this unobserved process that we defined. So this is indicated by this keyword distribute. The distribute means that GDP is an aggregated variable, and these terms actually refer to the disaggregated process underneath it, and the start of the aggregation interval is signified by this variable which is specified in this thing. So this specification, the with this specification, SSM procedure will do the proper disaggregation, will use a proper implied model and produce the desired out calculations and the out. So here is the desired monthly plot of monthly GDP. You can of course have it tabulated output in a data set, but this just shows you the output of the calculations. So these monthly numbers will be consistent with the observed data. So they will have used the information in the industrial production series and will have distributed the quarterly GDP numbers. So these numbers will sum to the quarterly GDP numbers, but for January, February, March months will add up to quarter, but they will have a pattern imposed by the available information. Okay, so this concludes the third example. Let's go to the final example. So in this example, we look at the data generated by a study that studied drug theophylline. which is used to treat lung diseases. 12 subjects were given different initial doses of this drug, and its serum concentration was measured at different times during the next 25 hours. The measurement times for different subjects were different and unequally spaced. That is, the data are longitudinal. So this study, we are modeling longitudinal data. So this plot shows the evolution of the serum concentration of this drug in these 4 subjects over time. So when the initial dose is given, it's not absorbed in the blood right away. It takes some time to absorb the drug to be absorbed in the body, in the blood, and after it has reached its maximum, our body starts excreting it and it gets eventually processed through our body. So a model called one compartment model describes this process quite well. And the one compartment model is commonly used in pharmacokinetic analysis. It turns out that the one compartment model can be formulated as a state space model. So before we go there, let me explain the particular model we will study in this example. So this model postulates that for any subject, this curve, this observed curve, can be thought of as sum of these 3 terms. The first term is a product of the initial dose and a common mean curve. This mean curve is, or the global curve, or is is implied by this one compartment model. The next term, C, is subject specific variation from this implied form. So this is what theory suggests the actual curve should be, but in a particular subject, the observed curve will deviate, and this is subject specific deviation. And then this is because the subjects may differ in their properties, or that particular days that person may have eaten something particular way, or whatever. And the epsilon represent another source of error, which might be the measurement error. So this is what the model is, and this model has a state space form. I'm not going to describe this state space form. I'm not going to go over the model specification this time. This example is discussed in this global forum paper I mentioned earlier. You can see much more discussion about this model and the state space form of this. I'm just going to quickly show you the estimated components, and here again I'm giving you the denoise, so a sum of the components. This process, the fitting process, you can get the estimate of this common term mu t, which is of interest to pharmacokinetists, but they also are interested in the subject specific denoised curve. So this is the plot. These are the plots for this denoised curve for 2 subjects. So the subject 1 was initially given a dose of 4.02 units. Subject 2 was given initial dose of 4.4 units, and here is what the denoised curve looks like for these 2 subjects. So you see that the SSM procedure is very flexible. It can be applied to a large varieties of sequential data, and in fact I have hardly covered the possibilities. So, but I think we need to stop somewhere. I want to thank you for staying with me up to the end of this tutorial. Because of the lack of time, I have left out many important topics such as model selection, details about parameter estimation, and so on. I still hope that I have given you some idea about the usefulness of state space models in general and the capabilities of PROC UCM and PROC SSM in particular. Both these procedures are continually being worked on. For the near future, I'm working on many initiatives at SAS as well as my personal initiatives. So we are working on readiness for cloud and distributed computing, readiness for streaming data, improved scalability, and many more features like keyword support for many more models. So there is a lot of new things happening to these two procedures in particular and many other things at SAS. So I welcome your feedback. You can write to me by email or use one of these uh, communities, SAS communities, to express your feedback, to give back. Thank you.